We have seen that if you have a one-dimensional periodic structure, so layered structure like this, and if you have perpendicular incidence, like so, then basically you always have a band gap. So the light will always be reflected 100%, provided you have an infinite number of layers here. Now, this is only true for normal incidence. As soon as you deviate from normal incidence, then you end up in trouble. At some point, the band gap will close, because if you look at the limiting case of incidence like this, in the horizontal direction, there is no periodicity at all, which can help to scatter the light, so you will not have a band gap in that direction. So this tells us that if you want a band gap for all possible incidence directions here in the plane, that you don't need a one-dimensional structure, but you actually will need a two-dimensional structure. And of course, if you want to take this one step further and also look at all possible incidence directions, not only in this plane of the figure here, but also in the entire three-dimensional space, then you need a three-dimensional periodic structure. Now, different compared to the 1D or a normal incidence case is that now it's not guaranteed that you will have a band gap. You will need to carefully design your periodic structure. So for example, one of the knobs you can tune is the refractive index contrast between the different layers. And then pause the video and think a bit about what would be the best case to get a good big band gap. Would you like to have a bigger index contrast or rather a smaller index contrast? So pause the video and think about this. So it's clear that a bigger index contrast is beneficial, right? Because if you have a small index contrast, in the limits of this index contrast going to 0, you basically do not have a periodic structure at all anymore. So you need a big index contrast with lots of reflections that can help collaborate to get a larger incidence range of angles that can get reflected. So the index contrast is an important design parameter, but there's also other things you need to look at. For example, the shape of your lattice. You want a triangular lattice, a square lattice, the shape of your scatterers. So all of these things are parameters that you need to take into account to carefully design your periodic scattering structure. And that basically tells us that we can no longer get away with using analytical formulas. We basically need numerics to solve all the properties of these higher dimensional structures. So what you then want to look at, of course, is band diagrams. So remember, for the 1D case, a band diagram was simply a plot of omega versus k, and we only had a k vector in a single relevant direction, and then you get plots like this, for example. So these are your band diagrams in one dimension. They're basically curves. Obviously, if you have a two-dimensional situation, then you also have a ky direction that you need to take care of. And then you don't have curves, but you have surfaces. Yeah, it's a bit difficult to draw. They look a little bit like this. So it's a bit more difficult to draw and also a bit more difficult to visualize. So again, let's not rely on my poor drawing skills, but let's have a look here at this computer-generated band diagram. In this case, this is for a two-dimensional lattice of dielectric rods in air. So basically a structure like this. And then what you see here are all these surfaces corresponding to the different bands. So if you look in the horizontal plane here also, you can see this triangle of the irreducible Brillouin zone. And then in this irreducible Brillouin zone, this diagram shows all the different bands that can occur. So there's a lot of information here. It's nice to look at, but perhaps a bit overwhelming. But one thing you also note is that, if you only focus on the edges of all of these surfaces, so basically the edges of the irreducible Brillouin zone, that basically gives you the information you need, right? Because you have basically a monotonous behavior if you go from one edge of the Brillouin zone, the irreducible Brillouin zone, to another edge. Nothing happens with like a maximum somewhere in the interior of the irreducible Brillouin zone. So based on this observation, people actually simplify a diagram like this. So what they do is they don't plot this 3D surface-based diagram, but rather they just walk along the edges of the irreducible Brillouin zone, along the edges of this triangle here, and then they unfold this structure and plot it in a form that looks like this. So then you get a diagram like this. So this is again our lattice, Brillouin zone, and the triangle of the irreducible Brillouin zone. And then you're going to take a little excursion in K-space. You're going to start at the gamma point, walk to the M point, then to the X point, and then back to the gamma point, and then plot how the bands evolve if you do that excursion. So you see that excursion over here on the horizontal axis. You move from gamma to M to X and back to gamma, and then you just plot that as if it were just a linear straight excursion, but it's actually, of course, you walk along the edges of a triangle that you have here. Okay, that already looks a bit easier to interpret here. You might also notice that there's two different types of lines. There's dashed lines and full lines, and they correspond to different polarizations. So the dotted line, for example, is the TM polarization. And the convention in these photonic crystal studies is that the M polarization in this case corresponds to the electric field that's parallel to the rod, so perpendicular to the image plane here. And then you see for these dashed lines that there is indeed a band gap over here where no propagating modes are present. So if you excite this structure with the M light, with the frequency in this band gap, you will get full reflection. You'll also notice that that's not true for TE polarization. So polarization is another thing you need to take into account if you want to design a nice reflector using this photonic structure, this photonic crystal.